a good way to go. All right. Yeah, so you're stressed about your final projects, and I'm stressed about your final projects. Okay? So we're all stressed together. A couple of notes. One, I barely, as you just saw, got back the preliminary I tried to give you reasonable feedback, on what I saw. A few things. Okay, one, from the grade perspective, I didn't have time to weight grades. So I'll let your groups know if you had, some peer evaluations that were not even, because there were some, and that's normal. So that will happen. But I guess other things, please use Word, right? Please use the shared folder that you were given, or that one of you was given, okay? And please only share, just copy the link, you're in Word Online, copy the link, paste that in, all right? Please, and make sure it exists, okay? There were a number where I had to dig back into the Microsoft forum to find. I was actually able to find a number of them, but there were some that I just couldn't find in my search. Okay. So please make sure your version history is intact. Many of your groups are probably seeing, hey, wait a second, what's going on? I can talk to you about some of the things that I saw, right? But I do go into the version history. TAs may not be doing that for your homework so much, right? I understand, because they've got a lot going on. But I am going to your version history, and if whamma-bamma, nothing's bulleted, and it just appears like suddenly, and it's talking about stuff that there's little possibility that we've covered, or that I would expect you to have covered. It's sus, okay? So, please, you must use the bullets until the end, okay, until your final submission. That's partially by design, okay? And I can talk to your groups about things, if you want to talk about it. Otherwise, let's just move on, okay? And get your outlines together. These are outlines until the end, and they should be essentially, how do you say it? The same exact length, unless there was some issues with this one every time. Okay. Yeah, it was. I've got a lot going on, so I was hurried in trying to get some of this done, and I hope that before your next outline is due, the next one, I guess, because there's one due very soon, that I'll be able to give you feedback and a little bit more time for that. Any questions? Any thoughts about this? Open to suggestions. By and large, I think the grade does not reflect the amount of effort, because I remember just like technical hiccups, right? But if you are, I don't know what the average turned out to be, but it was not as high as I was thinking it was going to be. All right. Yes, Paul.
We had an issue with how we shared it to you where you couldn't read it. Would that grade be changed, or is that kind of set in stone?
Send me a message, and let's talk about things during office hours. Okay. I can talk to you a little about things after class. I have to leave to get somewhere after, but I have a few minutes afterward. Right before class is tough for me to figure things out, because as you can see, I'm trying to figure things out, and so yeah, we can discuss. Good. In terms of what is happening and the due dates and things, so the demo simulation, right, that got postponed, that date is old, but it's upon us, right? Essentially it's 9. And then the session 17, that lab / post lab, that's due, I guess, a week from today, right? So you have material from our meeting today, hopefully, or if you wanted to get started, we could look at, could have looked at the past videos as well to do this assignment. And it's going to be a lot more involved than some of the other ones. That's why we don't have a good. That's should have an idea of how they guide you on these types of assignments. And then, of course, we have ourselves. Okay. All right, so question for you all. Why are we spending a whole session together, a whole class together on studying flow over a sphere? Well, did any of you study flow over a sphere previously in fluid mechanics? Is that a topic? Andrew, you studied it a lot? Why did you study it a lot, Andrew?
I was worried it would be on the final.
Oh, okay. All right. Okay. Do you want a commitment that it will be on this file? Because we could commit to that.
I think we'd like a commitment that it's not going to be on file.
Okay. Well, anyway, we'll see. All right. So, but why? Why are we spending time on this? Why are we spending time on this? It's super complicated. Okay, that's interesting. I typically have more reason for studying something than it's super complicated. But yeah, Parker.
I have a question. Why a sphere, not a cylinder?
Okay, good. So we could have done cylinders, all right? And in fact, cylinders are often useful for looking at vortex shedding patterns, okay? Because they, unlike what you'll see with a sphere, a cylinder will, in some regimes, actually create alternating vortices shedding off of it. So like one will shed, and then another will shed, and another shed. And cylinders are very important in terms of chimneys and other structures that are very large. If you've seen strakes, those are like the little windy thing that goes around them. If you go 95 and you look at, you start going up to Newark and you start looking at the stacks that are reading stuff, okay, you will sometimes see a straight line that grades up the vortices that would form that would cause oscillating behavior. So we could have done that, quite frankly. And I think spheres are, okay, well, you tell me, I'm asking you guys a question. Why are we studying spheres, though? Yes, Andrew.
Because if you're studying airflow over a surface, spheres are relatively simple because they're symmetrical.
Yeah, they're symmetrical, so we can do this with axisymmetric modeling. Okay, it is 3D. A cylinder is 3D as well, but it's kind of 2D. Okay, that's not necessarily a reason to do this. Complexity is not necessarily the idea. With a sphere, we have Stokes flow over a sphere, right? So Andrew, you studied it so much. Let's see. What do you remember what the equation is?
Because you can integrate, if you take it, you can integrate I think if you use the Navier-Stokes equations, you can cancel out a lot of stuff just because of the symmetrical exact nature of the sphere.
Okay.
Simplifies a lot.
Yeah. Okay. So we've talked about, I think, once before. It's proportional to velocity as opposed to velocity squared, and it's like 3 pi mu times the velocity times diameter. Okay, I think it comes up right there. Okay, for creeping flow for very low Reynolds number, this drag force is something that you can rely on. So one of the reasons why we do this is that we can have a ground truth, or something close to ground truth. Remember, when we look at convergence, there are multiple ways we can think about it. Okay? One is, how is my simulation getting closer and closer to a ground truth relationship as I decrease time, or as I use more increments for the mesh or the volumetric discretization. So it can help us to kind of test our simulations, which is what we're going to do today. they're also very well studied, all right? And if you're interested in looking at drag on an object, you can kind of approximate many objects as a sphere or maybe a collection of spheres. You could also do what Parker was saying, and think about using cylinders and then putting like a sphere, you could try to sum them up. This is very rough, okay? But if you're thinking about a skydiver and you want to approximate the drag on them, you could stick some spheres there and a sphere there and cylinder, or cylinder, right? And try to get kind of a rough approximation for what the drag might be. There's a bunch of experimental data, and it's pretty rich in terms of behavior and vortices and various things that you might be able to see. We're not going to see all the rich behavior that people have captured experimentally with our simple axisymmetric modeling, but what we will hopefully get by the end of the assignment is behavior that mimics what people have measured experimentally for the drag coefficient. Okay? So we'll talk about this in more depth, but here in this region, this is going to be a very low Reynolds numbers, and it's what you call creeping flow, so very slow. And it has this property of being 24 over the Reynolds number. So you know how to calculate the Reynolds number, you know how to calculate the drag force, and so this relationship out here is going to essentially be a 1-over relationship with velocity, and you're going to be able to see that until you get to, I guess, a reasonably turbulent flow. And we'll talk about what happens in some of these other regimes. There is already, well, let's keep going, and then we'll get to some of these details, all right, about the drag crisis and so on. So for very low Reynolds numbers, you have these nice images that, or nice drawings, I guess, that kind of describe what the field lines look like. So in this case, you see that they come around. You do have a stagnation point, and then it comes out, goes around. And at Reynolds number about 1, you still have about 10% accuracy. Okay, so it's not bad to be able to have this type of relationship. Now, where would you see spheres in a somewhat real-life experiment? Like, where, we already talked about that. I mean, you can put a head on somebody that's falling out of the sky, but where do you see, spheres in like engineering practice? Yeah.
I mean, it's easy to simplify something as a sphere, something that's more of a complex geometry.
Yeah. Okay. Okay. Where else? That's the general state. Yes, Safa.
You're looking at individual fluid particles.
Sure. So fluid particles, yeah, or sand, right? Now, there's a whole subject of granular matter when they start getting to lots of sand particles and things, but yeah, you could think of fluid experiencing drag. Yes, and your name is? Karen. Okay, yes, Karen. Yeah, so ball joints, yes. Now, that's absolutely true, okay? Those are spherical. Maybe I'll just rephrase the question a little bit. When do you see spheres in flow? Yes.
Spherical weather balloon.
Okay, so yeah, weather balloon, right? It has buoyancy because it has a lower density gas inside, or it's got heated air inside, right? Low density gas again. Yeah. So you would think about how is it floating up, and what's the drag on it? Okay. For a couple years of my life, I was fascinated with bubbles. Okay, so bubbles are also often spherical. Right? Any idea of smaller bubbles are often more spherical than larger bubbles. were interested in being able to remove bubbles from solution so that we could mold polymers. And we decided to look at spinning as a way of doing that. Right? So I was like shaking things with bubbles in them. My lab neighbor, office neighbor was saying, hey, why don't we try spinning? And that became the topic of the thesis. So what you see here is a diagram. You see there's an axis of rotation. And when it's not spinning, you can kind of get this idea, well, gravity is acting downward, right? But as this starts to spin faster and faster, you essentially have gravity acting outward. So if you have a bubble inside this kind of yellowish greenish region, which way is it going to go? Okay, so I don't know what this means because I'm looking at you and I'm looking at this. So does it go inside or outside? Why do you say outside? You want things to spin before? Yes, that's a good point. Yes.
Will actually go inside because it's lower density than the material it's in?
Yeah. Which way do the bubbles in your soda pop go? Against gravity, right? Okay. So because they have their density so much less, they actually come towards the inside of the mold, or the inside of the mold, and so you can have like this flat kind of liquid air interface, and there is a meniscus and whatnot, but then as things get spinning, the liquid air interface actually becomes vertical, and the bubbles move towards the middle. Now, what are some ways that you know of to get rid of bubbles if you have them in a liquid? Okay, so one is spin it like this, obviously, right? But what's another way you can get rid of a bubble? Yes.
Pull it back.
Okay. Yes. Okay, so what happens, so you can pull a vacuum. Okay, so have you done this before? Okay, what were you pulling it on? On water. Okay. So this is a very interesting, okay, so you can actually get rid of bubbles by both pulling a vacuum and applying very high pressure. Okay, so what are we talking about? Okay, so if you pull a vacuum, which who here has done some composite layup? Do we have any RFR people who do the composite layup? All right, so what do? What's your, after you put everything in the bag?
For composite layups, you're gonna get your carbon fiber, you're gonna get your resin in it, get it maybe a breather cloth over it, get it in the bag, and then you pull a high vacuum to try and evenly disperse the resin throughout the carbon fiber.
Right. Okay, so you try to get it to cool the fluid through, right? And you're also trying to get rid of bubbles, right? And you let it go for a little while. So why does that work? Well, you have a distribution of dissolved air in the liquid, right? So for example, if you going back to soda pop, right? You've probably seen some of these things where they put like a little piece of candy in, like a Mentos or something, and right? So after shaking, right? So and that's going to work better at a higher temperature. So by Henry's law, essentially the higher the temperature is, the less the water or the liquid typically wants to hold to dissolve content, right? Dissolved gas. So if you're in cold water, there's actually a higher dissolved oxygen concentration than in warm water. Okay, just like in steady state at a given temperature and pressure. Well, actually, the temperature is higher or lower. Okay, so what happens is as you cool vacuum, right? By Henry's law, you lower the pressure, and so the liquid cannot support as much dissolved air in it. Okay? So what happens in vacuum, when you pull vacuum, it actually pulls the water or pulls the air out of the liquid. And so you actually get bubbles. And then something interesting happens. As you keep pulling vacuum, you get mass transport and you're decreasing the overall concentration of dissolved air in that liquid. Okay. Air is air though. So if you have an air pocket, so now let's say that you have gone ahead and you've dissolved the concentration of dissolved air in the surrounding liquid. But now you have an air pocket. Well, that air pocket has concentration of air in it, right? And there's less air in its surroundings. So there's a gradient in the concentration of air, and so the bubble or the air pocket will want to dissolve. So a lot of the dissolution of bubbles when you pull vacuum happens either by the bubbles expanding and coming to the surface, or the bubbles actually going to whoop once you bring back atmospheric pressure. Okay? Now, if you're in the business of making toothbrushes and you're using injection molding, what's the opposite that you do? Well, you compress the living daylights out of it. Okay? You're trying to compress. And what happens there? Well, by the Laplace-Young relationship, right? So that says that as you increase the radius of curvature, the pressure has to be higher. You remember in mechanics and materials when we were doing pressure vessels, and there was that PR over 2T, right? And we said sigma, we call it stress, is equal to PR over 2T. Okay? Well, if you rearrange things a little bit, and you say, well, sigma is surface tension, and that's a constant. And you say, okay, sigma equals PR over 2T, that means that what's going to happen to the pressure? Well, you have sigma over R, okay? And that means, so as I decrease the radius, right, and sigma stays constant, or as I increase pressure, the radius has to get smaller in order to support, okay? And so the pressure gets larger and larger as you compress, obviously, and then what happens is that the liquid-air interface inside the bubble, Henry's law says, hey, I can dissolve a lot of air when you have high pressure. So if there's an air-liquid interface, at that interface, suddenly a lot of air will go into that interface. Once again, concentration gradient forms. Lots of air in the liquid-air interface, not so much air in the surrounding liquid. It's going to want to compress and dissolve into solution. Okay? So that was probably more than you wanted to know about bubbles. Okay? For us, what I wanted to show you is that you can see these bubbles moving, and you can see and calculate their speed based on their size, all right, and a little bit more information. So we all love the no slip condition because we can remember it, no slip, right? Well, at the surface of a sphere, a hard sphere, that condition is satisfied, right? So the velocity of the liquid right on the hard sphere, if it's traveling whichever or whatever, it's going to be the same as the velocity of the hard ball. But if it's a bubble, you actually don't have the no slip condition. You can slip. The liquid air interface, the velocity doesn't have to be zero right at that interface. And so there's this thing called the Hadamard-Brzezinski relationship that has been derived. And essentially what it says is that if you know the viscosity of the fluid and you know the viscosity of the gas or the bubble, okay, and the viscosity of the fluid is much, much greater than the viscosity of the bubble, you can get a new relationship or a modified relationship for this coefficient that goes in front of the Stokes flow relationship. And since the viscosity of the fluid is so much larger than the viscosity of the bubble, this relationship says that term is going to be 2/3. And so you have less drag on a bubble because the no slip condition is not satisfied. Right? It slips through the water. So, or slips through the liquid a little more easily. Right? Now, what I did is I stuck this liquid in a centrifuge, and that metal instantly turns transparent. No, that's just a different experiment. All right. So what you see is that this is a mold, and then I would put a plexiglass mold on the top. you could see slow motion of this device spinning. And you can kind of see after a few seconds that a lot of the bubbles have disappeared. And then we can zoom in and we take kind of close to 1 image per revolution. And what do you see? You see that the larger bubbles are moving really fast, and these smaller bubbles, they don't move as fast. And that's the balance of the buoyancy, right, and the drag on. Now, very large bubbles, because of buoyancy, are going to get whipped out of that mold very quickly to the center. Very small bubbles are going to be pressurized because that goes with density and it goes with density and omega squared, the speed squared, and the radial distance from the center squared as well. And so that pressure actually pressurizes small bubbles. So that, as we learned, right, if you have a small bubble, you can have high internal pressure because of, well, PR over 2T essentially. And that means that those bubbles are going to collapse. So which bubbles are the hardest to remove? Huh? The what?
Teeny tiny ones.
Okay, so the teeny tiny ones, they dissolve. The teeny tiny ones, they dissolve into solution. Yes. Yeah, the medium one, right? I said the large ones come right out, the teeny tiny ones go right in solution. So it's the medium-sized ones, right? So the medium-sized ones, what they do is they're in the mold and they're kind of confused. They have drag force going on them, and the pressure is actually decreasing as they get closer to the middle. And they're the ones that will they'll essentially want to dissolve exactly when they reach the area. So they're moving along, they don't go away, but they go kind of slowly, and they just are the pests that want to get to the middle. They survive. They don't die because of pressure, and they're not carried out because they're too small. And so that is cool. If you like, we can talk about it in more depth, but we did experiments, and we have a simple model that shows that yes, in fact, if you think about bubbles of a critical size, which tend to be on the order of 100 microns or so, those are the ones that are going to be most difficult for that particular process. You have a different process with vacuum and pressure, the bubble, the critical size. So the bubble, the critical size of the bubbles will be different. Okay. Essentially was a case where we were able to use turbulent flow. Okay. The bubbles were so small, and the speeds were not that great that we could say that was turbulent flow with this modification of the Hadamard. Now, what happens if you get a little bit faster flow? Okay. Well, you can get what they call the donut. Right? So you can get these rings or these vortices that are going to be circulating on the back of the sphere. I do not have images of this. It would be cool. I'm sure they exist. And then you can get a little bit faster, you can get these donuts going back and forth behind the sphere. Again, we're not going to simulate this behavior. It'd be very nice, but we're not going to be able to do it. Okay? Once you get a little bit faster, all right, we get into this kind of transition phase, and there start to be the shedding of these vortex rings. And then finally you get, or maybe not quite finally, but you're gonna, as you get to faster, okay, before you get to this drop off, you're gonna start to have separated flow, and it can become quite turbulent. And there's another dimensionless number. Did they ever talk to you about the Struve-Hall number? Maybe not. Okay. So this is a dimensionless number that can give you an idea of the frequency of any type of, well, fluid process. And it's based on the relationship between length, velocity, and frequency. So people have done experiments and they say, hey, you know, if you're between 800 and 200,000, this true hole number is going to be about 0.2. And so you can actually predict the frequency of shedding. I wouldn't build a clock on this, but if you wanted to, you know, you could look at the frequency of the vortices coming off and try to use that as some type of mechanism to keep time. Okay? And then they have documented all kinds of, well, maybe not all kinds, but different types of shedding of vortices. So you might have this vortex ring, you might have a vortex tube, you might have a waving wave, you might have an omega-shaped vortex. Okay? So experimentally, people have been able to do these characterizations. And as you know, you're going to have to be very careful. You're going to have to be very smooth, and you don't want to have people jumping around when you do these experiments to shape the floor. Now, what happens when you get a little bit faster than 200,000? You go through something called the drag crisis. Okay. And this drag crisis means that the coefficient of drag actually drops. That's kind of nice, as you see here. And in addition to that, it's dependent on whether the surface is smooth or rough. So if you want to induce this drag crisis at a little bit of a lower Reynolds number, maybe you want to drop off the surface. You may end up, depending on where you are, you may end up with a lower coefficient of drag if it's smooth, as you see here. Now, what's kind of interesting is that this drag coefficient stays flat, which is good for you and me. If you're not thinking about the drag here in terms of, you know, a ordinary differential equation that you're going to solve. The drag coefficient stays kind of flat, and that means that you can look at this relationship, meaning the increase of force versus the Reynolds number, or force versus velocity, as being parabolic. So in the assignment, what you're going to see is that I asked you to first do lower Reynolds numbers, okay, very low, and then you're going to end up going to a turbulent flow. And I don't expect Ansys and you to get a real number. I don't expect you to get 0.5 as that drag coefficient, but what you will see is that if you plot the force versus the velocity, it is parabolic. Why is it parabolic? Well, it's parabolic because that's how, if you have a constant drag force, then it's, if you have a constant drag coefficient, then the drag force has to raise. Parabolic. Okay, flow about a sphere, a little bit more about this. We have coefficients of drag, we have multiple regimes of flow, we have effective roughness. Surprisingly, I don't know what's up, but the Magnus effect doesn't seem to be very popular this semester. A lot of times people like to do this for their projects, but I don't know, maybe it's fallen out of favor. So in COMSOL, you remember how we specified the no slip condition? Well, you can actually specify velocities. And you can actually, if you want, you could specify like a speed for the wall of an object. And so that would be an opportunity to implement the Magnus effect if you so desire. Okay? So when you have a ball that's moving in a flow, well, you tell me, what is the coefficient of lift for a ball that is in a flow? Someone in quadrant 4. What do you think? Coefficient of lift for a ball in a flow, or sphere in a flow? Okay, coefficient of lift for an airfoil that's completely symmetric at 0 angle of attack? Yes. It's 0, right? So if you have a symmetric object, right? This is, you know, send me a check if they ask you this in an interview question, okay? All right. So if I don't think I'm allowed to say that. All right, don't do that. All right. But anyway, so if you've got a symmetric object, right, in a flow, the streamlines are the same above and below it, and so you're not going to see a net force. Now, with vortex shedding, which we've talked about a little bit here on spheres and definitely on cylinders, there's actually this alternating in cylinders in particular that will shed on the top and shed on the bottom. So in those cases, you can have an oscillatory behavior of force, but the net over the steady state force is just going to be 0. So why do we make symmetric airfoils? Like, well, yeah, you can change the angle of attack. That changes things, right? Okay, that'll change too. Okay. Same thing here. If the ball is spinning, okay, then you can have a change in the flow behind it, and you can cause either lift or drag. So golfers take advantage of this all the time, apparently. I don't really golf, but they hit the ball, they spin it, it's spinning as it comes off. And because of that, it's able to take an upward trajectory, and then it'll come down. So a golf ball doesn't take a parabolic trajectory like maybe I don't know, some other object that you could throw without spin. So just kind of interesting. I think maybe 1 or 2 people were doing magnets related things, and I got feedback. I said, hey, you might want to consider it. Okay, so now what we're going to do is a simulation in COMSOL. Right? Now COMSOL actually has a special physics for modeling creeping flow. Okay, well, creeping flow is very slow. So this, right? Reynolds number less than 0.1. So in that case, if you go back to Navier-Stokes equations, which we all love, you see on the right there is this inertia and times the total derivative. And if you break up that total derivative, you get the light blue there, and you have this convective acceleration term, and you also have a dv/dt term, or a partial v with respect to t. That's acceleration. So what happens when you implement the creeping flow physics? This inertial term, okay, all this goes to 0. Okay, essentially all of this goes to 0. So you're just left with, assuming you don't have gravity, you're left with the gradient of the pressure, and you're left with this divergence of the shear stresses, or the viscosity times the velocity of velocity, which is this expression. So why would you want to do this? Well, if you can assume you have creeping flow, you don't have to solve for the acceleration. And you could potentially have a more accurate, faster, or at least faster simulation, and you let fewer issues with convergence. So what we're going to do is we're going to show you how this works in COMSOL, and we can all think about how nice sometimes it would be to do this in COMSOL afterwards. And then we'll do the same thing in Ansys afterwards. Okay? So what we're going to have here is a axisymmetric geometry with a bubble or half a bubble cut out, or half a ball or half a sphere cut out. We have the viscosity of water, okay? And you know, often we're just using material properties that are given to you in the software. We don't have to only use those properties. I mean, I've had it before where someone's like, I can't find the material properties for this material in the COMSOL database. Like, well, you know, you can search online. not like you can't put in custom values. Okay, so we'll see how this works. But in COMSOL world, axisymmetric is vertical, and in Ansys world, axisymmetric is about the horizontal axis. Okay, so we're going to have a geometry where we're bringing the flow on the top, and then it comes out the top. Now, if we do this calculation for the drag force, so this would be the 3 pi mu times the velocity times the diameter. For a bubble, or sorry, for a sphere of about 100 microns in radius, in diameter, or 50 microns in radius, this comes out to be something like 0.94 nanometers, or 940 kilonewtons. So let's go ahead and let's see if we can get this to work. You'll see, you know, and now you can say, I've at least seen it and a little bit exposed to it. And this class, it used to be COMSOL based, right? But now it's Ansys based. And this is not the most recent version of COMSOL, but it's an academic version that we've actually paid for that our lab has. So we're going to go ahead. We're going to do a 2D axisymmetric problem like this, and we're going to go into fluid flow, and we're going to do single phase flow, and there it is. There's a creeping flow right there. Now, you could get excited and say, hey, you know, what was really interesting or what's fun about COMSOL is if you have a set of partial differential equations, you can actually put in the coefficients, or you can put them in the weak form, right? Remember the Galerkin method, finite element analysis and all that stuff? You can put them directly in here and you can work on solving them. But they have a lot of things already set up because not everybody wants to do that when they have a creeping problem to solve. Okay? So now we're going to do stationary, which is the same thing as steady state in Ansys. And now we're in. And I don't need Grammarly to check my grammar right now. Okay, so let's go ahead and change the units to be microns. And we'll start working on the geometry. So for this geometry, we'll put a circle, and we'll call it radius of 50 microns. And we can hit build selected, and it just puts it there. And then we'll go ahead and we'll add a rectangle to this geometry, and we can have the width, we'll say the 200 microns, or 0.2 millimeters, and the height we'll say will be 1,000 microns. And we can put the base of this up at like 700 microns. Is that right? We'll see. Oh, I think I put it way above. Yeah, so let's see, 300. It probably needs to go. There we go. Except that's the Z. The width. Oh, center. That's why. No, that's. Hold on. Basic geometry, folks. All right. So the circle is it has radius of 50. Nope. That's why. Okay. That is why. Okay. And we'll put it. All right. Almost there. Almost there. Yes, that's the geometry that we want. All right, and then we will go ahead and we'll do a Boolean, where we're going to do a difference, going to be our geometry. Put it a little more center. All right, so we can also come in and we can select a material. So for this, we need to have material here, so we can do add material from the library, and we're just going to bring in water. So liquid water is what we use. And now that's there, and it has functions for the viscosity and the density, but it should be about what we said for at 0.001 Pascal seconds, about 1,000 kilograms per meter cubed, regular standard temperature and pressure. Okay, so creeping flow, we need to put an inlet. So we'll put the inlet at the top, and we need to do an outlet bottom, and we'll go ahead and we will we have the axial symmetry here, but we need to add. We can do either we'll do an open boundary on this side. That. And also symmetry could be another option. They come out a little bit different, but those are options. Okay, we're going to be looking at the steady state solution, so we'll keep that stationary. And then for the mesh, the default is not bad actually. Okay, so we'll do more detailed mesh for our simulation in Ansys. You can kind of see that it has some layering happening around this already. Maybe and it's, I want to say physics control. All right, so let's let that be. And let's go ahead and run it. Select that. All right. Oh, why is everything 0? Any ideas? Well, I didn't specify the inlet velocity, right? So I got to come back over here, and I'll just do normal inflow velocity, and this is up and I'll put 0.001 value, 1 millimeter per second. All right, and so here we have it. Okay, you can kind of see this is a velocity, right? So you can see the velocity kind of dies down as we get here. And you can even do a little 3D like thing here, like that. That's kind of fun. You can see the pressure, right? This is the stagnation point up here. It comes back as you get further, or it goes back down as you get further away. All right. Now, often we're interested in the drag coefficient, right? So what we're going to do is we're going to go to the derived value, and we're going to do a line integral, and we're going to come in here and we're going to go under the creeping flow, look at the auxiliary variables, come down and look at the total traction, right? And we can use the z component of it, so that's the vertical component, and bring that in, and we're going to bring in these edges right here. All right, and then we hit evaluate, and what do we see? All right, so we get 0.76 nanometers, or nanometers, right? It's not exactly, well, what value were we supposed to get? We were supposed to get 0.94 nanometers, okay? So this is one of the things where we're on the right order of magnitude, just kind of throwing things out there and seeing what we get. Now, if we change the we can change a whole bunch of parameters here. But for example, one thing that's going to be relevant for Ansys in a little bit is looking at convergence as you change the width of this domain or the height of the domain if it were to be rotated. So what we can do is we can come over here pretty simply and change our rectangle to have a width. Let's say we make it 400. And then we build all these objects. So now it's larger. And we haven't talked, and this is the first time we really kind of talk about it, is that if you change the domain size for fluid flow experiments, it can change what you get for your calculations. So remember that was around 0.76 nanonewtons, and now if we go ahead and we evaluate it again, we're on the opposite side. Now we're heavy. Okay? Now we're at 1 nanometer, or 1.06 nanometers. All right? So you're starting to see, and you'll get to see this when we do it in Ansys, that by changing the geometry of the mesh, we can have a pretty significant impact on the values that we're calculating. So the other thing that maybe this shows us is that I'm not fretting too much if my value is not exactly what I want. Okay. Now, if you're doing a very precise measurement of fluids, you are still very happy if you're just on right order mapping. Okay. And so you'll see that. We'll experience that in a little bit. All right, so let's go ahead and close COMSOL. And we're going to do the same problem now in Ansys. So in Ansys, we're going to turn things sideways, and we'll change things up a little bit. We're going to have 200 microns from the left inlet to the center of the sphere. And we're going to have a mesh size of 5 micrometers. We're going to have some inflation. We're going to be a little bit more careful. Inflation around the inner edge. And we're going to have a total domain length of 1,000 micrometers. And one of the things that you're going to get to do in your homework is change the height of the domain and see how that affects the drag force. Right? So this is something that you might want to do for your convergence assignment, your convergence checkpoint in a little bit, if you're doing a fluid flow about an anomaly. So here we go. We're going to pull up Workbench. Oh wait, I'm nervous. Oh, don't do that. Okay, Workbench student, yeah. That's no problem. I have like 3 versions of Ansys on my computer right now. And just hoping it can make it through the semester. On that note, if at least throughout this semester, I do suggest that you stick with 2025 R2. They update them like every 6 months. And you can get the 2026 version now, but the computers in the lab, those are using 2025 R2. So if you want to be able to create something in 2020 on your own computer as a student, and then bring it into the lab, actually I guess you could do it either way, to be honest, because it's bad with the pattern, at least with things that we're doing. But once you run it, often once you run it like in the academic version that we have in the labs, you won't be able to open it again on your computer. So keep that in mind. And I ran into someone on the hall and were like, oh, so we have the VDI, virtual desktop, right? If your computer is resource limited, or if you're finding yourself, I really want more time in the lab, well, we had an issue with the lab a couple years ago, and that's why it's now got closed doors after hours. Okay, so the solution to that is to use the VDI. It's not using your computer's resources; it's using a virtual machine's resources. All right, so it's quite powerful. Anyway, so if you find yourself, I hope you're not finding yourself. Please try to keep it so you don't have so many nodes in your simulations for your projects. But if you do find that you need a little more power than you've got, please use the VDI. All right, here we go. And if you need more power than the VDI provides, or the computer labs provide, your project is out of scope. Okay, that's what happens there. All right, so we're going to do a fluid flow fluent problem, and we're going to come over to geometry, and we're going to change it to 2D. All right, and we're going to do a space plane geometry. here. And I'll just remind, as that's coming up, I'll just remind you of the geometry that we are attempting to create in space. And I'm going to show you how you can parameterize now the height or the distance of this top boundary from the bottom, so that you can do this type of convergence study, a study on convergence to suicide. Okay, so once again, we're going to click on the Z. We're going to click on this. Oh, what happened? No, don't do that. Okay, we're going to click on this. That was what I did wrong. On that plane, and we'll go ahead and put a circle there at the origin, and we'll make it 100 microns in diameter, and that's larger. Okay, and if I should have said this, oops. Okay, so I've already changed. Oops. Oh no, maybe did I change it? Was it 100 microns? So what I should do, what you should do, is you should come into space plane options. And for your units, oh, I'm in millimeters. That's not good. Okay, so now I've got that's not cool. All right, so it's already, I think I may have gone past the point of no return. So we will just go ahead and proceed in microns and hope for the best. But you should go ahead and you should change this option here to microns beforehand, and it will let you do that, but I already punched it. And you can also go in, I'm not sure how much this matters, but you can use type tolerances too. Okay, so we'll change this, or we'll just, probably easier, we can do either one, we can dimension, right? We can click on dimension. You see it's 100, but we need to make it 0.1. Okay, so now that shrinks everything down. Quite a bit. Oh. I can't remember which one is which, but there we go. Okay. So that's 100 microns. Then I'm going to make a rectangle. I'm going to put out, start here. Okay, maybe I have to start it out last. This might be interesting. Because it only wants to. Okay, so we'll do that for now, but I'm going to change that dimension. Well, this is really great. Okay. Undo. Zoom out. Shift. Move over. Rectangle. Okay, here, let's do rectangle. Yes, that is a rectangle. Okay. And what we're going to do here is define this dimension right here to be 0.2. Millimeters. This dimension right here to also be 0.2 millimeters. And this dimension over here to be 0.8. Like that. Okay. All right. So it's a little bit awkward, but I think everything's okay. This time we will go ahead and click and sketch. All right, and then you've got the surface. Oh, Okay, so now I'll go ahead and change to micrometers, which I should have probably done before. Okay, and now I'll go ahead and I'll put this like I want it at 100. Okay, and then now we'll go ahead and make the rectangle like we want it. And how much time do I have to spend on making a box with a circle and 200 there? Okay, and then this one will be 800 this way. Like that. Beautiful. Then the thing I forgot to do is we're going to trim. Trim all that stuff away. And now we've got the geometry we want. And then we hit and sketch. That's the geometry we want. Now, in order to parameterize this top surface, what you want to do is you want to click on Move. Come over here, you left click, then you left click on the green, and then you come over to this little thing that says like little dimension, you left click on that, and then we dimension to this bottom surface, left click there, and then you click on the P. And now that's created a parameter. Okay? And so now, if things are good, we should be able to exit. And we see that there's a parameter. So if you come over here to the parameter set, now you see that I can control the height of that object. All right, let's do the meshing. We'll go ahead and get in there. The mesh is going to have some features that we've used before. We're going to use the mesh size of 5 micrometers. We're going to have a distribution along the inner edge of this geometry that's going to have a 1 micron spacing. We're going to inflate. We're going to have 10 layers to capture what's happening at the boundary. And we're going to need to define the inlet and the outlet, the axis, which is also reserved name, and the no-slip inner edge, and the top, which we'll call essentially outer curve. Okay. Ooh, what's going on? That was interesting. That was kind of interesting. Okay, so it's always good, at least for these types of simulations, when you come in and you click on geometry, you make sure that there's only one geometry. We come over here, we select this edge, and we can hit N, and then type in inlet. We can come over here, select this edge, and hit N. We call that outlet. We come over here, and we hit this region, and we hit Shift, that region. Oops, maybe Control. Yeah, that's good. And then we can hit N, and we'll do axis. Right. This one we'll call inner edge, N, inner edge. And this one up here we'll call outer mirror. Okay. So we should have our 5 name selections. Inlet, outlet, axis, those have to be exactly as they are. And these other 2, we have the options to mess with. We come over and we mesh. What we're going to see, what do you think you're going to see? You're going to see like this nice, really open mesh. Okay? It's not going to capture everything we want it to capture when it's calculating on track. So what can we do? We can change this. Oh, and yes, this one did remember what I wanted, and it's in metric micrometers. All right, so make sure you change that. Here you're going to do 5 micrometers. When I say you, I mean you really will do this, because this is part of the assignment. And then you're going to come over here and you're going to do a method, and we're going to use primarily triangular. So first we had to select the geometry, this, apply, and then we're going to come over here, instead of quadrilateral dominant, we're going to do triangular, triangles. Okay, and then the next thing that we can do is go ahead and discretize the inner edge of this. So we can come over here. This is the face. So we can select this face like this, and then it's apply. And then over here we can nope, that's not right. Okay, what I want is the inner edge. My bad. So you go to name selection, or you could do edge. But if I do the name selection, I've already got inner edge in here. And for this element size, I'm just going to do 1 microns. If you click on this, you would be parameterizing this. We don't need to parameterize it at this point. For the growth rate, we can, what does this say? 1.2? Okay, that's fine. We're going to leave this as this is. All right? That's been discretized, and then we're going to inflate, okay, to add layers on this edge. In this case, yes, we will click on it first, apply, and then we could, I'll just show you how to do it the other way. You can do geometry selector, and you can do edge, and you can do it like this, or you could come over here and you could do the name selection and do inner edge. Either way is fine. Okay? But it has no selection now, so that's not good. So come back over here, select it, hit apply. Okay, for the number of layers, we're going to bring that up to 10. And then for the inflation, or the growth rate of the inflation, what happens when you have lots of inflation? Well, we've been talking about inflation in our country for a long time now. Okay? It means things grow faster. So if I decrease the inflation, that means that everything will be closer. Each layer will be closer to the next layer. So we're going to have 10% inflation, which is a lot if you're trying to save any money. All right. So then, at this point, we should be able to generate the mesh. And if we click on the mesh, it looks pretty good. That's a nice mesh. All right. Down here, if you look at the statistics, you will see that the statistics are a little bit different than in prior versions. At least my experience was a little different than prior releases of Ansys, but whatever. We're in the right ballpark. Unlike space-time, it's not bad to hit the update button. And so now it's moved the mesh into the workbench, and we can then open up our friend Fluent. I'm running out of time. So we double click here. This comes up. We can use double precision, and we can use a few processors to hopefully get faster, more accurate results. And we're going to want to initially run simulations with Laminar Flow. So, unbound path, that will be fun. Let's see how things go. It may not, we did all that goofing around with the geometry, the space-time. It may come to haunt us. And if it doesn't work, what do? You do it again. But I'm not going to have time to do that for you. So for us, what we'll see here, we should be able to just, well, okay, we can do that way. So we're going to make our system axisymmetric like that. We're going to be doing steady. And for our models, we're going to have the energy off, and we're going to change viscous to laminar. Okay. We're going to come down to our material, and we're gonna go into fluid, and we're not gonna do air, we're gonna do water. So we click new, and then we bring this Fluent database up, and we're gonna scroll all the way down. We're gonna use the water liquid, not the water vapor. We're going to copy that over, and we're going to close this. We're gonna be like, hey, what happened to my liquid? Well, I click over here, I hit change create, close, and we should be good with having now one of our materials is water liquid. We need to assign that to the cells in our simulation, so we come over here, and we will go ahead and edit, or double click, it'll be faster, and we're going to change that to the water liquid material. Watch, close. For our boundary conditions, we already have an axis that's set up.